Does this question look familiar to you from the beginning of the year? Or beginning of this unit? We started talking, I pushed the book up to the wall. When we did this problem in class, the example I showed you is me pushing the book up the wall. Does that sound familiar to you guys? It should be in your notes someplace. When I pushed the book up the wall, it was pretty easy to determine that the frictional force had to be downwards. I want to talk to you about static friction for a bit today. Is it plausible that I could push the book against the wall and it not move at all? Is that plausible? I mean, so, and I'm not trying to make this complicated. If I have a book and I push it against the wall, I can just hold it there, correct? Is it not unreasonable that if I push too hard, it'll start to move up the wall? But if I don't push hard enough, it moves down the wall? That means that there's a minimum and a maximum force that I can apply and a range. If I stay in that range, the book doesn't move. But if I push too hard, the book goes up the wall. If I don't push hard enough, the book goes down the wall. That sounds like what we just saw? That all seemed like reasonable kind of conversation? Is there an amount of force I can apply where friction's not required to hold the book in place? And the answer is yes. In fact, when I asked this the first period, they had the same look in their face that you have now, but that could be a test question for Thursday. There's absolutely nothing wrong with me asking that specific question. In fact, I want you to find the answer. Let's say the book is 2 kilograms. How much force do I have to apply at 45 degrees to hold the book in place without relying on friction? Let's say the wall is super slippery and there's no frictional force between the book and the wall. How much force do I have to apply so the book just sits there without friction? So anybody who says they don't know where to start has not been in class for the last 2 weeks. You should know exactly where to start. I'm going to come around and see what you've done. I'm trying to get a handle on where you are with all this. But just good work. For the most part, I saw a lot of the right stuff out there. A few of you, though, I don't know what the issue is. Is there a force acting downwards? What is it? Gravity. So you'll forgive me if I'm frustrated with a few of you. Is it in contact with any surface? Yeah. What kind of force would that provide? And has to be perpendicular, right? The wall sideways? Okay. So we have these two forces, normal and weight. And is there an applied force that I have to use? Yeah. And I don't get any choice here. They told me how to draw it, so I'm going to have to draw it the way they gave it to me, right? 45 degrees, that way. So any of you who weren't able to do this, look, brings me no joy, but the quarter ends soon. So whatever's going on, fix your problem. Just don't make it mine. What it means, tell your parents you're going to be in trouble. Don't make it my issue. All right, so we all done? There's no friction in this problem. That was the whole point. So if I want to hold the book in place, I have to apply a force that balances what we see here. And I'm not trying to be difficult. This is perfectly acceptable for a test question, right? It was, in fact, I'd say that this one was somewhat easier than some of the questions we've had. So this is going to be cosine 45. This is FA sine 45. I only care about the y direction, so net force in the y direction is going to be 0. FA sine 45 minus 20 equals 0. So FA equals 28 newtons. Sine of 45.707. This is not the question I'm interested in. This just gets us started. But if I push with 30 newtons, right? If the book doesn't move when I push with 30 newtons, what direction must the frictional force be? Trying to get you to think. No, it's hard. If I push with more than this, and friction is going to try and hold the book in place, what direction will friction have to be? Just point. It's either up or down. It's not hard. It would have to be down, right? I'm pushing upwards more, friction will have to push downwards. And if I push at, say, 25 newtons, what direction will friction have to be? It will have to be upwards, sure. Which means there's a range of forces that I can apply and the book could still stay in place. That's what static friction is about. Static friction is an inequality, which means friction will spontaneously appear and will increase to meet the demand to hold the object in place. And it will increase until it reaches a threshold. The threshold is when this is an equality, right? The equal sign. But until that point, as an inequality goes, if I just push a little bit, well, there'll be a little bit of friction to hold the book in place. If I push a little bit less, well, there's going to be a frictional force to hold the book in place. And that will begin to increase until I reach the threshold. In fact, what I want you to do real quick is draw me two pictures. Draw a picture of what happens if I push too hard, and draw a picture of what happens if I push too soft. Assume there is friction. If I push too hard, what will it look like? What will the direction of the frictional force be? And if I push too soft, what will it look like? What will the direction of the frictional force be? Your picture should reflect that other forces are affected by your change. If I reduce the size of that applied force, I am also reducing the size of the normal force. If I increase the size of that applied force, I increase the size of the normal force. All of those forces are changing. And friction is based on the normal force, so it also changes. If we take this to an extreme, this represents two possible conditions. The minimum applied force is the smallest force I can apply before the box slides down the wall. And the maximum applied force is the biggest force I can apply before the box slides up the wall. Now, you guys have a tendency to think that I'm showing you like this firm example and every problem is going to be this problem. That's not true. You have to bring your skills to bear. All I said was we're going to be dealing with a case where the force is less than 28. What will that look like? Well, that's going to look like a frictional force upwards to hold the box in place. You should have been able to draw that picture. And if I push harder and the box still stays in place, then I'm applying more force than 28. Well, there's got to be a frictional force downwards, trying to keep the box from sliding up the wall. Now, you guys are sharp. If I tell you that friction is equal to, less than or equal to, mu times the normal force, and I tell you that mu is 0.3, you should be able to figure out what this maximum and minimum are. Try it. Try one. Try finding out one of these. You know the number's got to be greater than or less than 28. So if you get a 500, you're probably wrong. But try it. Just set it up. Just do the force concept model and set it up. Your pictures are correct now because I've drawn them for you. Only got 4 minutes, so I don't have a lot of time to wait for you guys. I'd like to reach a conclusion here. You realize that net force in the x direction is the same for both of them? Not the same size force, but the same relationship. Fa cosine 45 equals the normal force. That's going to be bigger on this side than it is on this side, but it's the same relationship for both. The normal force is based on how hard I push into the wall. That's all that says there. However, on the minimum side, if I look at the net force in the y direction, I've got Fa sine 45 plus friction minus the weight equals 0. On the other side, we've got Fa sine 45 minus friction minus the weight equals 0. Right, the only difference between these is one sign. One indicating the force is upwards, one indicating the force is downwards. But it affects everything else. Now, this is still the same problem we just did on this practice test. We know everything except for 3 things. We don't know the normal force, we don't know the applied force, and we don't know the frictional force. You need another piece of information, and you have it. You have that friction is less than or equal to mu times the normal force. In fact, you were told that mu is 0.3. Before you can use this, you need to ask yourself if you're at a threshold. Are you able to use the equality here? Are you looking for a maximum or a minimum? And you are. You want to find the maximum force you can push upwards. That means when the friction is the strongest in the upwards direction. And the minimum force that you can apply for it to slide before it slides downwards, that's the biggest friction can be, but when it's pointed up. This part of the problem, where you do some substitution, not all that interesting, but you're going to have to do it to find the answer. So you've got a couple things here. I would probably do some substitution there, and then use it here, and then use it here. The answer ends up being something in the low 20s and something in the 40s. You should practice. You should practice. There's 1 minute left, so I'm going to end there. We're going to be playing around with this frictional thing more, but we are going to be adding some stuff to it.